Laplacians on graphs.
Thank you. Thanks very much for the introduction and for the kind invitation. Also, as James has pointed out, I'm actually not here for the spectral graph theory program, so I'm actually a bit out of my depth here. Nonetheless, I hope what I talk about would be of a little bit of interest to you. So, so the motivation really is, well, by the way, I should thank Cheyenne and Yuan. Some of this work joined with them, and I learned a lot from discussions with them. So, so what I'm going to talk about, essentially, it's about how you can do spectral graph theory when the norm is not a 2 norm. Okay, so spectral graph theory. Well, if you view it in a certain way, right, like what I have on the slide, is that you look at the graph Laplacian and you look at the Rayleigh quotient of the graph Laplacian, and of course the norm that you use in the denominator of the graph Laplacian, that is a 2 norm. And the bilinear form on top, well, it's bilinear or quadratic, so it's a 2 tensor. The graph Laplacian, you're viewing it as a 2 tensor. It takes a pair of functions on graph to scalar, so it's a 2 tensor. And this talk, we're going to be talking about a case where the norm is something other than a 2 norm, P norm, okay? And where the tensor is something other than a 2 tensor. So we're going to look at like Laplacians defined on alternating D tensors. We're going to look at Laplacians on hypergraphs, which would not be a 2 tensor. Okay, so basically that's what we're going to talk about today. It's going to be a very light talk. This is the last talk and probably I think the only talk in the afternoon. So I'm just going to entertain you, amuse you a little bit, hopefully, and we can all go for dinner afterwards. Well, maybe not even dinner, for tea. Okay. Yeah, so the thing is, why is 2 so prevalent? Why is it, the de facto norm and the de facto order of the tensor when you talk about spectral graph theory? Well, so partly it's due to this observation by Jean Lawler. So Jean Lawler was a professor here at Berkeley many years ago, and he likes to talk about this thing, the mystical power of 2-ness. So in fact, when he passed away, there was a memorial volume, and the title for that, I guess, or maybe one of the article in that written by Lenstra, is precisely the mystical power of 2-ness. So he made the observation, of course, some of this observation, that many problems in computer science are easy if you have 2, right? 2 coloring is easy, okay? 3 coloring is hard, right? As soon as you change from 2, it becomes difficult. 2-dimensional matching is easy, 3-dimensional matching is hard. So of course, hard can mean NP hard, or it can mean something else, right? So if you talk about physics, you have 2-body problem and 3-body problem. One is easy, the other one is hard. So likewise, for Ising model, well, and in statistics, actually I just learned this from Cheyenne last night. If you look at a James Stein estimator, again, the phenomenon arises when you go from 2 to 3, right? And today we're going to talk about 2 norm and 3 norm, okay? So of course, why do you use the 2 norm? 2 norm is easy to compute, right? If you do like 3 norm, or in fact, any norm that's not 1, 2, or infinity, that is going to be NP hard. And likewise, my favorite example is that if you look at matrix problem, right, 2 tensor problems, in some sense they are all easy, right? Polynomial time algorithm, you can bound errors, you can bound accuracies, you understand a lot about them, but once you go from 2 to 3, it becomes difficult, okay? Right. So, however, why should we look at instances when it's not 2? Okay. Well, so of course, the computational intractability is going to be an obstacle, but we are not going to look at things just from the perspective of computational tractability. Of course, I understand that's primarily the use of spectral graph theory. Sometimes you can get insights, okay, and even if something is not tractable computationally, okay. So, and that is the point that I would like to make here. So let me give you 2 examples, okay, one from each of this program. The first one from the spectral graph theory program, the Cheeger constant of a graph. So the Cheeger constant of the graph, well, I guess is the number of cards, right? You break a graph out into 2 pieces, to partition into 2 pieces, and you look at the number of edges that run from one to the other, and you divide by the minimum of the volume of each of this piece, and you look at this minimum over all possible partition of the graph. Okay, V is the vertex set of the graph. Now this is very well known, right? It's first studied in differential geometry by Cheeger, and I bet you have seen it like 50 times in this week's program. Okay, or maybe right even in previous week's program. So this is, I would say, it's probably fair to say that this is a central object of interest in the spectral graph theory program. And well, what about the other program, the one that I'm participating in the algebraic geometry program? Well, one of the main objects, okay, is something called a permanent. Okay, the permanent is a, well, even if you're in the spectral graph theory program, you would have heard of the permanent. Okay, one reason is that this is one of the most successful use of spectral graph theory is to estimate the approximate the value of a permanent on a 0-1 matrix. That's the, stochastic matrix. That's the result of one of our co-director of this institute. Okay, so the permanent, of course, is a notoriously difficult object in multiple sense, right? It belongs to some of the hardest complexity classes. And of course, it's also of main interest in this. It has rich geometry, okay? And it's one of the main object of interest in the other program, the algebraic geometry program. Now, the thing is, so I'm going to try to say why is it that it pays to look at norms other than two norms, and why does it pay to look at Laplacian operators other than those that are two tensors, okay? So let's look at the first one. So one major use of the Cheeger constant is that it appears in something called the Cheeger's inequality, okay? Well, in differential geometry, the Cheeger constant, this Hg, or Cheeger number, is used to understand the second eigenvalue of the, the Laplace-Beltrami operator on the manifold, okay, or the Laplacian on the manifold. In spectral graph theory, it's used in the opposite way, okay? People are not interested in the second eigenvalue of the Laplacian. What they're interested in is, in fact, the Cheeger constant itself. So they use this to study but it's NP hard to compute, so they use this relation, the Cheeger inequality, to approximate the Cheeger constant, okay? So it's bound between, two simple functions of the second eigenvalue of your graph Laplacian. Well, the thing is, of course, this is a very nice inequality. It's used, for example, it's used to approximate the permanent, right? However, it's an inequality, so it's not so nice, right? Ideally, I prefer equality. So what if I insist that I have to write the Cheeger constant as an equality, right? Now, with some eigenvalue. In fact, if you work really hard, you can actually show that the Cheeger constant is the second eigenvalue of the one Laplacian, okay? And this is actually proved recently. A lot of people, I guess, suspected this, or maybe it's already known. But what I learned this from Casey Chang when I was in China earlier this summer. So this is, I'll say this is very interesting, right? You can actually say that the Cheeger constant is an eigenvalue and not just bounded between two eigenvalues, two functions of the eigenvalues, okay? So what is here? So here's an example where the one Laplacian appears, okay? The one Laplacian is the Laplacian with respect to, in some sense, so I should say maybe these are called nonlinear Laplacian. On manifolds, they are very well known, okay? The P Laplacian is the divergence of the norm of a gradient f raised to the p minus 2 power times gradient of f. Okay, that's the formula over there. I guess is this? Yeah. And so when p is equals to 1, that becomes actually a quantity that's non-differentiable. Right. So what? And this is the manifold version. It's very, very well known. So what Casey Chang did was to extend it to graph. Okay, in particular the one Laplacian on graph. So it's if you take the co-boundary operator, something that we're going to define later, that's the edge vertex incidence matrix, and you compute this thing, okay, of a function. Okay, take the matrix that represents the co-boundary operator. If you take the B transpose B, that gives you the graph Laplacian. But if you take B transpose times the sine of BF, okay, this sine is the sine function, okay, the derivative of your absolute value function. And it's going to give you the one Laplacian on a graph. So the Cheeger constant equals precisely to the second eigenvalue of this Laplacian. So I think that's may not be useful. That just says that this is hard to compute, right? Well, if you want to view it from the perspective of how people usually use spectral graph theory. However, it's insightful. Okay, so I know that the Cheeger constant really is some eigenvalue.
What does it mean, the eigenvalue given?
Yeah, that's a very good question. So of course, the thing is, one of the main theme that I'm going to talk about in this lecture is that eigenvalues, of course, is defined for linear operators, right? So this is obviously nonlinear, or the P Laplacian obviously is nonlinear. So how do you even talk about eigenvalues? So what I meant is eigenvalue in the sense of what people in PDE, okay, right? That's the folks who study P Laplacian would do, or people in optimization theory. What are eigenvalues? Eigenvalues are Lagrange multipliers. And viewed from that perspective, you can define, in fact, later on we'll see it, you can define eigenvalues for all kinds of stuff, okay, including nonlinear operators, including tensors, and things like this, okay?
Can you explain a little more what this sign of BF is?
Sign. This is the, so the sign of a function. This is, of course, non-differentiable optimization. What is the sign of a number? The sign of a number t is going to be -1 if t is, of course, negative. It's going to be +1 if t is positive. And it's going to be an interval, -1 to 1, if t is 0. So this is a set value function, okay? It's not a function in the usual sense.
But BF is not a number.
No, it's going to be a set. So that is why it's so, that's why people didn't predict the definition. This is sort of the right definition. If you want sort of the second eigenvalue to be equals to the Cheeger constant, then this has to be the one. Okay.
That's why you you don't have a different motivation for this. I think it's
so of course it's also
it's trivial once you define this this thing on the second.
Sure. That's right.
So it was defined just for this purpose, or?
Yeah, I guess the thing is, there's a so I'm not exactly sure it's trivial. Okay, I haven't quite digested the paper yet. I'm happy to show it to you later. The author sent me a preprint.
Happy to show it to you after the talk. I think it's okay.
Yeah. Okay. So, but anyway, this is not going to be.
That's why. So BF
component-wise.
Yeah, it's component-wise, of course. Yeah, you do it component-wise if it's a vector. Yes.
Okay.
For that result, can you also say something about the Cheeger cut and the eigenvector?
The what?
The Cheeger cut to the eigenvector.
Oh, okay. So the thing is that. Yeah. So, well, the thing is I have to get back to you on that. That I do not know. Okay. Yeah, but anyway, this is meant to be a motivation, right? So this is motivation for the spectral graph theory folks.
Laplacian also has meanings in terms of higher dimensions, which
Yes.
you're not using, right? So, because I understand one Laplacian from the last talk was something to do with
yes.
two-dimensional objects.
Okay, so the thing is, I'm going to use the word one Laplacian in multiple ways. So this is the nonlinear one Laplacian, and later I'm going to talk about the Hodge one Laplacian. Okay, that's the one that will be used in, later on. Okay, and that's the second part. That's going to be when I formally start to talk. This is sort of just motivation. And well, another example, right, for the algebraic geometry folks, right? Well, maybe it's not a question that you would naturally ask, but let's say we ask this question. Well, so the permanent is, of course, a homogeneous polynomial of degree n in n squared variables, right? The entries of a matrix. So in that sense, it's that's equivalent to saying that it's a symmetric n tensor, a tensor of order n. So you can write it down in coordinates as a hypermatrix, okay? So it's a n squared by n squared by n squared, okay, n times matrix. And the, so the thing is because of the fact we wanted to make sure that it's symmetric, the entries are, it's non-zero, okay, it's constant when it's, when you have that property, when the indices are precisely equals to one of the terms that occurs in the monomial. Okay, so the point, you may or may not know this, but symmetric tensors have eigenvalues, right? And it's defined precisely in a way that, and I explained to Andrea. So this is, and we'll look at this later, but just take it on faith right now. So eigenvalues, as I said, are Lagrange multipliers. So in that sense, symmetric tensors have eigenvalues. So what are the eigenvalues of this very important object, right? What are the eigenvalues of the permanent when you view it as a symmetric tensor, okay? Now the thing is that it would appear to be a pretty daunting problem. However, if you can use graph theory, well, and graph Laplacian, or rather hypergraph Laplacian, then you can actually solve this quite easily. You can find all the eigenvalues. Okay, you can view the permanent tensor as the adjacency tensor, just like you have a graph, you have an adjacency matrix. You have a hypergraph, you have adjacency tensor. Essentially, it's an n-dimensional matrix with ones whenever you have hyper edges and 0 elsewhere. Now the thing is, the eigenvalues of, well, you can make some observation and use those observations to find the eigenvalues of these permanent tensors. Okay, it's a joint work with Shenglong Hu, my postdoc.
Interpretation of what those eigenvalues are?
Yeah, so the thing is, the largest one is going to be essentially the spectral norm, right? It's there are, you can count them. It's an interesting problem in algebraic geometry. Giorgio Ottaviani has done some very significant work in this regard. So it's sort of, the way I would say it is that it enhances your understanding of matrices, okay? So like, you can talk about characteristic polynomials. And, yeah. Well, so I do not know of any actual use, okay? But I do know that it gives you some insights, okay? So like, you know, you can ask various questions. What's the analog of a characteristic polynomial? How is it related to, for example, the hyperdeterminant and stuff like this? Okay? Yeah, so the first part is, well, this part actually has two parts. That part that you just heard was part 0, motivation. And the first part is about Hodge Laplacian, and it's sort of just providing sort of some easy aspect of Cheyenne's talk early on in the day. So I'm going to tell you about Hodge Laplacians and cohomology, but in a, well, really, really simple way. Okay, so I think this is going to be the simplest. Well, I should say that it came from this lecture that I gave at the thanks to Cheyenne, right, at the meeting where I'm supposed to explain like this kind of things to people with no background at all. Okay. And a sort of scientific American level, okay? And this is the result of that. So I hope it would interest you or amuse you a little bit, okay? Now, what is cohomology? Okay, this is cohomology in one slide. I challenge you to find something that's easier than this, okay? Now, the thing is, let's suppose that we have two matrices. I'm not going to tell you what they are. Let's just say two matrices, m by n, m by p, so you can take their product. And let's say the product is 0, okay? So this is, well, freshman linear algebra, well, maybe even high school linear algebra, that if you have this relation, that if the product of two matrices is 0, then the image of one must be included in the kernel of the next one, right? The image of B must be included in the kernel of A, right? Otherwise, AB cannot be 0, right? And the thing is, in fact, this is even only if. And since these are subspaces, you can say that image of B is a subspace of the kernel of A. And what is cohomology? Cohomology is the kernel of a quotient image of B, okay? Just the quotient space of a vector space by its subspace. Okay, this is cohomology. Okay, homology, exactly the same, except that you have different A and B. Okay, now next thing is Hodge theory. Okay, again in one slide. What is Hodge theory? Okay, essentially, there's another way to do it. Okay, if you don't like quotient space, which I don't, right? Because quotient space means you have to deal with elements that are equivalence classes, so it's sort of hard to represent them, right? If you want to do computations with them. So can I find an actual element well, a vector instead of a equivalence class of vectors? Well, it turns out that you can. Okay, so the way is to use the Hodge Laplacian, right? Hodge Laplacian is to take the two matrices that we had previously, A and B, where AB is equals to 0, and from this this product. Okay, this is the Hodge Laplacian that Cheyenne was talking about earlier. So it's A star A, right? A star is the adjoint of A. Well, you realize that it can be formed. Well, it makes sense, right? You know, this is going to be a n by n matrix. Now, the kernel of this matrix, the null space, is precisely the cohomology. So I could have defined cohomology to be the null space of this Hodge Laplacian, okay? Well, and furthermore, it gives you insights. You know, there's something called Hodge decomposition. We'll see this again later. It says that the space, well, the domain of A, or if you like, the codomain of B can be decomposed into an orthogonal decomposition. Every vector in Cn can be written as a sum of 3 vectors, each orthogonal to the others. And furthermore, the piece in the middle, the cohomology, the kernel of A star A plus B star, is the intersection of the kernels of A and B star. Okay, very, very simple. Everything can be, you can give this as an exercise to your undergraduate in your undergraduate linear algebra class. In fact, I do that. Okay, so now the thing is, of course, something that's so simple, you know, it's hard to impress people, so you have to come up with big names for all these objects. Okay. So that's essentially what algebraic topology is, to give names to this stuff. Okay, the matrices A and B are called co-boundary maps. Okay, elements of Cn, you call them cochains, right? And when you have the map like this, you call it a cochain complex, right? Co-cycles, co-boundaries are the elements of kernel of A and image of B, respectively. And you can say that an element of kernel of A, a co-cycle, is co-closed. Element of co-boundary is co-exact, right? It's the last two relation. Cohomology classes, you can either view them as the elements of the quotient space, right? Kernel A, quotient kernel by image B, or you can view them as harmonic cochains. Okay, that means view them as elements of the kernel of the Hodge Laplacian. The Betti number, of course, is just the dimension of either one of these spaces. Okay, so that is algebraic topology. Okay. Well, so the thing is, of course, this is spectral graph theory. So let's see how this is relevant to graphs. Okay, so of course, I didn't tell you. You know, one thing that I left out is what are A and B, right? So of course, it's not true for any two matrices A and B where the product is 0, right? It has to be some. The topologies are interested in specific A and B, right? They have many different ways to define this matrices A and B. And you know, this sort of this gadget that I talk about here, right? This construction here gives you cohomology classes. Okay. Now, so let's look at graphs and see how this is relevant to graphs. Okay. And then, so the and of course, you know, you heard Cheyenne talk early on, and this is exactly what he was talking about early on. So let's say we have graphs. Okay. So graph is. Every graph gives you a simplicial complex. Okay, so what is that? That means if I have a graph, usually it's built out of vertices, right? Zero-dimensional simplex, right? That's a scary word that topologists come out for vertices, and one simplices, right? That's edges, and again, a word that topologists used to call edges. And there are triangles or three cliques, right? That's called two simplex. So the thing is, a simplicial complex is something that you can build out of objects like this, where you glue simplices along faces. Okay, so that's a simplicial complex. So every graph gives you a simplicial complex. Every simplicial complex gives you a graph, right? How's that? You know, it's very simple. If I give you a graph, all I do is I fill in all the cliques. Okay, then that gives me a simplicial complex, right? For instance, if I have a triple vertices and there are edges all around, I fill in that, right? That's a three clique, right? It's a triangle, so I fill in. I assume that it's a triangle there. If I have four of them, four vertices, that forms a complete subgraph, I fill in that tetrahedron, so that becomes a simplicial complex. And likewise, given a simplicial complex, I just remove all the simplices of, all the interior of simplices of dimension higher than 2, and I get a graph. So it's 1-to-1, okay? So graphs and simplicial complexes are essentially the same, okay? At least in this picture, right? Now, so I'm going to call KG this sort of this simplicial complex is called a clique complex, and what I'm going to say next is going to be so this is just I haven't related to what I was talking about earlier. So now what are your cochains? Right? Remember that the functions in the elements in Cn are called cochains, right? We have here, right? Cochains is just a term for the elements of Cn. But what is Cn? Okay, so here's what a Cn. Cn, of course, is a vector space, right? You know, if I don't choose bases, I can make it abstract. So these are all my possible choices for Cn. I can look at the functions on vertices. I can look at the functions on edges. I can look at the functions on triangles. Okay, of course, I can go higher up. We'll come to that later, but let's start from 1, 2, and 3, right? I'm going to look at special types of functions, right? Because I want my edges undirected. So I want my functions on edges to be, well, it's going to be a function on a pair of vertices. But since my graph is undirected, I'm just going to decree that the value of ij is equals to negative of value of ji. Okay, this is an alternating matrix. Okay, skew symmetric matrix. Well, how about the functions on triangles? Again, that's a function on triples or vertices. And again, I'm going to require it has this alternating property. When I do permutation, it's going to change, the sign is going to change according to the sign of the permutation. Okay, there's a skew symmetric pre-tensor. Okay, when physics, right? So that's these are just the, I can view this as potential on the electric field, right? Or a tensor field, right? On the space. In topology, they're just called 0, 1, 2 cochains. Okay, so those are the elements that your matrices A and B act on, right? Of course, since these are finite dimensional, it's automatically the space of this 0 cochains or 1 cochains or 2 cochains is going to be Cn for some n. Okay. Oh, okay. I use real here, right? So if I use complex numbers, then it would be Cn, right? But let's say real. Let's move to real from now on. So what are the co-boundary operators? What are the A and B that we talked about at the beginning? Well, so in topology, again, they have special choices for A and B, right? So I'm going to use freshman calculus language instead of topology language. So co-boundary operators essentially are finite difference operators. Okay, discrete derivative. So the gradient of a function, right, on the vertices is going to be a function on the edges. Okay, and that function is given by simply taking the function on the, let's say S is your function on your vertices, and I'm just going to take pairwise difference of that. So that is gradient. Okay, it takes 0 cochain to 1 cochain if you like. Okay, and I put L2 just because there's an inner product. So I'm just by right I should write CC0 K. Okay, but let's be vague. Likewise, you can talk about the next derivative that takes what B is my grad, A is my co. Okay, and so A times B co grad. That is going to give you 0, right? So that is very nice. So this gives you candidates for your matrices A and B, right? Because co of grad is 0. You can also define things like divergence, right? We need something when we talk about Hodge decomposition. We needed something called the adjoint of our A and B, right? So the adjoint of gradient is going to be something called divergence, and it's denoted diff. Okay, so grad diff co are sort of a I guess some of the most basic objects that you learn in vector calculus. So this exactly just basic stuff. Well, the graph Laplacian, right, in this sense, is just the diff composed with the grad. Okay, the if you like B star B, right? And if you look at the next, the one Hodge Laplacian, okay, the sort of the next order, the next object that's above the graph Laplacian in this picture, that is what I would call the Helmholtz operator, what people normally call the Helmholtz operator. And what is that? That in this notation, its language is negative grad diff plus co-adjoint co. Okay, so this is so we know, for example, from that first 2 slides on topology, that the kernel of delta 1 is going to give you your 1 cohomology. The kernel of delta 0 is going to give you your 0 cohomology. Okay, so now the thing is, what about higher up? So higher up, the thing is, I have to bring in some topology language. So you can look at alternating functions on any k-dimensional simplices. Okay, and these are called k cochains. And likewise, you can define co-boundary operators on this. I can put inner products on this cochain complex. That's why I write L2. And the boundary operators is defined precisely by an alternating sum. So if you look at the special case, k equals 0, 1, and 2, you get your operators grad and diff. Okay, grad and co. Okay, 1 and 2. Right. Well, so the fundamental theorem of topology, and that is the first equation I've introduced in this part of the lecture. That's AB equals to 0. You take two matrices, and the product is equals to 0. Okay, that is, in some sense, the fundamental theorem of topology. Okay, it says that the boundary of a boundary is null. Okay, if you take imagine any geometric object. Okay, look at its boundary and look at the boundary of the boundary. You see that it's going to be an empty set. Okay, this is sort of the opposite. The dual of that. It says the co-boundary of a co-boundary is equals to 0. Okay, and once you have this, as we saw earlier, it immediately allows you to do all this stuff. Okay, define Colmology, define Hodge Laplacian, and things like this. And this is exactly what we do, right? So the next thing is to follow what we did earlier, but now in an abstract framework. With this, you can define the combinatorial Hodge Laplacian. Okay, and this is what Cheyenne was talking about earlier. And the Colmology classes would are precisely the kernel of this, as we saw earlier. So those are called harmonic forms. Okay, this is harmonic cohomology cycles. This is nice because you have an actual function on your simplices or a vector that represents your cohomology classes instead of a whole equivalence classes of them. And there's a Hodge decomposition theorem, just like what I said earlier, except that this is now rewritten in this slightly more abstract language. Okay, and this can be easily proved using simple linear algebra. Okay. The case of greatest interest, right, for application, which I won't talk about today, because I guess Yuan might say a few words about this tomorrow, so I won't say more about this. So is the case where k is equals to 1, okay? When you look at functions on pairs of vertices or functions on edges. Now the thing is, this Helmholtz decomposition or Hodge decomposition for k equals 1 is actually useful, okay? You can use it to study problems in rank aggregation, or can use it to study problems in game theory, which Pablo did in this wonderful paper. Okay, so this is stuff I won't go into. And anyway, both of some of the authors are here. Pablo is here, and Yuan is here. You can just ask them, right? So what about relevance to this workshop? So I know that, of course, this workshop people are interested in using spectral graph theory to solve all kinds of difficult problems. Like, for example, you want to solve a linear system or linear programming problems in time that is better than what is currently known. Of course, the other workshop, the algebraic geometry workshop, is also interested in this problem. How do you invert a matrix in times as O n 2 plus epsilon? Well, of course, that's slightly different flavor. Okay, this workshop is interested in how to use spectral graph theory to do it. How can I invert a matrix or solve AX equals B in a either exact or least square sense by exploiting, ideas from spectral graph theory and doing it in nearly linear time. Okay, well, so of course there's the amazing work of Spielmann and Tang, and lots of other people have done work since then. But anyway, these are probably the origins. Well, so how is it relevant? Well, one thing is that if you look at this notion called Ricci curvature, okay, you're given a simplicial complex, or actually a graph, you can define something called the Ricci curvature. Okay. Now, by the way, I should say that one of the key ideas in this Spielmann-Tang approach is that whenever you have a diagonally dominant symmetric matrix, okay, you can view it sort of as a graph Laplacian, and using this, you sort of could use spectral graph theory ideas to invert that matrix in almost linear time. So the thing is, how about higher order Laplacian? Okay, so the relation is that, well, let's say I want to do this for higher order Laplacian. Of course, what you gain by looking at higher order Laplacian, first of all, graph Laplacian must always be the usual zero. Graph Laplacian must always be a positive semi-definite matrix. But higher order graph Laplacian actually removes that. Okay. You no longer have that requirement in any matrix. Essentially, I guess you can represent it as some higher order graph Laplacian. So you can do this for higher order graph Laplacian. You could actually invert any matrix, not just symmetric diagonally dominant matrix in nearly linear time. Okay. So one example when this is possible is when the Ricci curvature is positive. Okay. When it's non-negative. When the Ricci curvature is non-negative, you can actually do this. But that, of course, relies on the result of Spielmann and Tang, right? Because when the Ricci curvature is non-negative, delta 1 is actually diagonally dominant and symmetric. Okay, this is sort of ongoing work that I'm talking about with Yuan and Cheyenne. So, but right now this is all I can say. What if the Ricci curvature is not positive. Okay, that's actually the interesting case. That would be the case that's not covered by Spielmann and Teng. Okay, second part, hypergraphs. Okay, this is the part where I talk about the permanent. Unfortunately, I didn't have time to finish this part. Okay, so I only have. I would tell you a few things, right? But won't be able to get to the permanent thing. Okay, so this is current joint work with a postdoc, Shenglong Hu, whom I mentioned earlier, right? So this is sort of a bit different, but still the element is the base element is actually the graph Laplacian, okay, and its eigenvalues, just like before. So, well, if you have a symmetric matrix, this is where I'm going to talk about defining eigenvalues when you don't have a linear operator. So, of course, you have a matrix. You can view the symmetric matrix. You can view the eigenvalues and eigenvectors as the critical values and critical points of your Rayleigh quotient. Okay. Well, or equivalently, you can view it as a Lagrange multipliers. You can write down the Lagrangian for this problem and say that you want to constrain the denominator to unit norm. Okay, and unit norm in a sense of the L2 norm. Okay, the 2 norm. Not. So if you write down the Lagrangian and you write down a KKT condition, you're going to get your usual eigenvalue, eigenvector equation, okay, this one here. And what are your critical Lagrange multiplier? Those are precisely your eigenvalues, okay? So the moral here is the eigenvalues are Lagrange multipliers. And this is sort of a pretty well-known thing, right? If you study nonlinear eigenvalues in PDE, that's exactly how they view what they mean by nonlinear eigenvalues. Now, so this also allows you to do it for tensors. Okay, this is nonlinear. Okay, the tensor is, so I'm going to use the word tensor a bit loosely. What I meant is a tensor with coordinates. A proper term will be hypermatrices. So this can be done for hypermatrix. Okay, n by n by n three-dimensional matrix that is symmetric. Okay, meaning that aijk doesn't depend on the indices ijk. You can permute in any order and it would give you the same value. Now, you can look at the cubic Rayleigh quotient, take a cubic form, right, define in the numerator of this thing, and divide by, and normalize it, okay, by the L3 norm, so to speak, okay. Well, so there's, of course, here's where you start to have a bit of ambiguity, right. So the L3 norm, if I put absolute value, that's exactly the L3 norm, that's nice. Well, except that it won't be algebraic, okay? So it's so the thing is, if you put absolute value, the techniques of algebraic geometry wouldn't apply to this anymore. You cannot use that to study. And if you want to use that to study, right, like what Luke and what Giorgio did, this problem, you have to use the algebraic L3 norm, meaning you leave out the absolute value. Let's do that for now, right? Actually both are useful in different ways. Actually, you can use the L2 norm as well, but I won't get into that. So the L3 norm, this gives you a sort of something that's scale independent, right? If you have a ratio of something cubic to something cubic, so your Lagrange multipliers, your eigenvalues, are going to be scale independent. So this is nice in that sense, okay? But L2 norm is nice for other things. If you look at you carry out the same thing, right? Look at a KKT condition of this constraint optimization problem. It's going to give you an equation that looks very much, that's sort of the analog of your eigenvalue eigenvector equation, except that now it's going to be a quadratic system rather than a linear system, okay? Now,
is this, because what Giorgio and Luke do is coordinate independent.
Yeah.
But you said yours is coordinate dependent.
Yeah, so the thing is, for example, this would not be preserved by. So I guess what Giorgio did was to look at the eigenvector, okay? Right. So that can be written down in a coordinate independent way, right?
No, but we use the L2 norm.
L2 norm, yes, there's that too.
You defined the same concept.
Yes, for L2 norm, that's right. L2 norm is, yeah. So, well, as I said, when you go from 2 to 3, suddenly things becomes more complicated. You're going to go from a 2-tensor matrix to 3-tensor, a hypermatrix. Suddenly things becomes ambiguous. There's really like, you can use L2 norm, you get something interesting. You can use L3 norm, you get something interesting too. Like for instance, using this notion, I can prove a Perron-Frobenius theorem for 3-dimensional, in fact, k-dimensional hypermatrices, right? If these are non-negative matrices, there's a Perron-Frobenius theorem. It's exactly like the one that you prove for matrix. Again, that's using this L3 norm. If you use L2 norm, you can get something else, right? For instance, I would say that Luke and Giorgio has this amazing paper that actually uses this concept to find tensor decomposition, which is
These
yeah.
only for real numbers?
It's over complex. Okay, so yeah, so of course you know that if you have a real symmetric matrix, the eigenvalues are real. That you lose that, right? As I said, you go from 2 to 3, it becomes harder. So you lose that property when you go to a hypermatrix. So when you have a high order tensor, its eigenvalues, even if it's symmetric, the eigenvalues can be complex. Okay. So how does this apply to graph theory? Of course, right? So this, last couple of minutes, I'm going to talk about this. So it doesn't, okay? But it applies to hypergraph theory, okay? So if I have a hypergraph, that's a generalization of a graph. Instead of we have vertices as usual, but instead of edges, we talk about hyper edges, okay? So there's a collection of k element subsets of V. And it's undirected, so I don't care about the order. Now, so a hypergraph is called, okay, I'm not going to need this. Well, actually, I'm not going to talk about the next part is not going to be useful too, because I won't get to that. Okay, so but anyway, there's this notion of a k-partite k hypergraph where you can partition things into k vertices where each edge intersect only with one of this partition set, or with one of this Vi, okay? It's just like a bipartite graph or a two-colorable graph. Now the thing is, this kind of, why is this of interest? This is of interest because the permanent tensor is k-partite, okay? And this is the relation we use to find its eigenvalue. But I won't get to that. I'm out of time and I don't actually have the slides. Okay, okay. So the adjacency tensor or the hypermatrix is going to be, well, you know, if I give you the name and I tell you what an adjacency matrix of a graph is, you would come up with this definition, right? So it's going to be a symmetric tensor, n by n, if it's a 3 hypergraph, where it's the value is 1, aijk is 1, if that edge is there. It's just an indicator function of whether an hyper edge is present in the hypergraph, okay? And of course, each one of these hypermatrix is going to define a cubic form, okay? I write AFFF. So this cubic form divided by that sum of the Fi, okay, or constrained to the L3 sphere, where the algebraic L3 sphere is going to give you your eigenvalues, okay? Reminder from the last slide. Now, so why is this useful, okay? This is useful because instantly you can prove some very basic result that parallels what you have in spectral graph theory, okay?
Is that non-additive?
Nope. Nope.
So by no means in a product.
Yeah. So this is not a norm, as I said. Okay, this thing can be 0. Okay, so they can. Yeah, that's why it's not. It's well. So if you put absolute value, okay, then you get compactness. If you then, but it becomes non-algebraic. It's not a you cannot study using algebraic geometry anymore. But if you don't put absolute value, then it becomes non-compact. But to the upside is that you can use algebraic geometry.
In the definition of L3 norm, you do need the
absolute. Yes, of course, right. So yeah. That's why, you know, when it's odd order, actually it departs from, when it's even order and real, it's fine. But when it becomes complex or anything, then this actually, even the L2 norm, where you have sum of squares instead of sum of absolute value of squares, things becomes different, okay? Yeah, so, but let me not get into that. So, you know, well, these are things that you can prove. Well, in fact, I thought I proved them. And I realized that, you know, a few years later when I was giving a talk that, you know, this actually, Joel Friedman and Viggerson actually had almost the same thing, okay? Almost the same thing in a paper that's published long ago, okay? So it tells you in some sense that these eigenvalues I define, well, you may not believe that this is the right way to define eigenvalues. Why should I use the L3 norm and not the L2 norm? Why should I not use the absolute value? Well, the thing is, it gives you results like this, okay? So as far as spectral graph theory or spectral hypergraph theory is concerned, this is sort of right, okay? Now the thing is, so this is the part that I would not have time to finish, okay? So this is the part that would be related to the permanent. So you can, just like in spectral graph theory, sometimes you don't want to work with the adjacency matrix. You want to work with the normalized adjacency matrix, okay? And the normalized adjacency matrix can be just almost as easily extended to tensors, right, for hypergraphs, right? The thing is that you need a k minus 1 factorial that becomes 1 when k is 2. And instead of the square root of di dj, you need the well, the geometric mean of the product of the degrees of your vertices, okay? So this is, when k is equals to 2, this reduces to your usual normalized adjacency matrix. And of course, once you have this, you can define normalized hypergraph Laplacian and stuff like this. This was actually studied by my postdoc in his PhD thesis. Okay. Well, so the thing is, what is this? But again, if you view graph theory as discrete differential geometry, if you view a graph as a discrete analog of your Riemannian manifold, and this is actually the analog of actually using the graph Laplacian is at least on a manifold, or rather the manifold Laplacian is going to be given by this, right? If you look at this actually defines the manifold Laplacian. This is sort of your co-boundary operator. Well, on a graph, when everything becomes discrete, this gives you the square of Fi Fj, right? The finite difference thing that we were talking about earlier, the grad. Now, if you raise this instead, well, this is still the 2 norm, but if you raise this to the p power, okay, the 2 norm to the p power, okay, then the discrete analog of this thing, okay, on a manifold, I don't know whether it's been studied in manifold, maybe it is, okay, gives you actually it gives you this, okay, gives you the normalized hypergraph Laplacian here. So it's sort of a discrete version of what you would expect on what looks pretty natural on a manifold, right? Except that this, of course, how do you define the gradient of a let's say, for instance, a 3 simplex, okay? It's actually the finite difference definition. Okay, so I guess I'm out of time. Well, so anyway, I ran out of, I couldn't finish my slide, so this is where I stopped. So the result that we need to find the eigenvalues of a hypergraph of a permanent hypergraph of the permanent is based on this one. Okay, this is a very basic result in spectral graph theory that says that if the graph is bipartite, you can split it into 2 sets with edges only running from one to the other. Then the spectrum, okay, or the eigenvalues must be symmetric. Okay, meaning that precisely this. Well, there's an analog for hypergraph. Okay, it's actually my PhD thesis, but I didn't publish it. But it's been published by Joshua Cooper and his co-author. And the observation is that a permanent hypergraph is an M-partite hypergraph. Again, using this relation, and then what Shenglong Hu and I did was that we wrote down actually equations that characterized when this would hold, right? And certain other things. And with that, you can actually find the eigenvalues of your permanent. Okay. Yeah. Thank you.
Question. Can you find the eigenvector of determinant and permanent also for L2 norm?
Oh, L2 norm, I do not know. But the eigenvector, so the eigenvector of your permanent tensor, right, are precisely your permutation matrices, okay? So you think of the, so let's say I look at this thing, okay? The permanent tensor, the eigenvectors of this are precisely, well, depending on how you view this, right, let's say, well, in a concrete way, you take any permutation matrix and stack all the columns. You get a matrix of dimension n squared. That would be an eigenvector of your permanent. Right?
And for the determinant?
The same, almost the same, okay? But the eigenvalues are different. You can also write down, you can also ask the same question for the determinant. Yeah, but that's a bit trickier, okay? Because that's, you have to do something before it becomes this one is automatically an adjacency tensor, of a hypergraph. For determinant, because there's a minus sign, right? There's a sign in there. So you need to do something before it becomes an adjacency tensor of some hypergraph. Okay? Yeah. Yes.
Can you delineate, can you say more about your solver, your one Laplacian solver? I didn't understand the hypothesis.
Oh, okay. So the thing is, there isn't one yet. So if we want to do this, I guess, is there an actual implementation of the Spielmann tank?
But I didn't understand the hypothesis.
Okay, so it's the same. So what I was suggesting was that, if you want to get rid of this condition, right? So essentially, this is by representing a matrix A, right, that is symmetric, weakly diagonally dominant as a graph Laplacian, roughly speaking. That's how, I guess, they did it, right? But if you want to get rid of that condition, let's say you want to get rid of the diagonally dominant condition, how can you do it? So one way is to, instead of looking at graph Laplacian, which is always going to be positive definite, you can look at higher order Laplacians, which would not have that property.
So the
Yeah.
simplest, just you have,
Yeah.
the simple case would be the graph only has triangles and edges.
Yeah.
And there's some condition here about what the graph has to the property.
So what I'm saying here is,
One Laplacian, is that right?
yes, if you want to solve the one Laplacian, one way is to use the Spielmann-Tang algorithm.
Oh, okay, this is your first definition, not that.
No, yeah, this is the no. This is the precisely this definition. Okay, this one. Okay.
Right? Helmholtz Laplacian.
Yeah, Helmholtz. This one. Okay. If you want to solve this equation on a graph, okay, you want to invert this operator on a graph in nearly linear time. You can do it if that graph has non-negative Ricci curvature, okay, according to that definition that I
So the
put.
problem we had is how do you simply find the flow on the edges that meets the demand? I mean, when you work it out,
Yeah.
you need to be able to find, a circulation that meets the demand, a circulation demand. Right?
Uh-huh.
How did you just find that, let alone?
Well, I didn't do it. Okay, it's sort of as I'm discussing with collaborators, Cheyenne and Yuan, but I actually haven't done this. It's just that based on this is sort of I can tell you what is true. Okay, if the combinatorial Ricci curvature is non-negative, then the graph Helmholtzian, okay, this one Laplacian is going to be diagonally dominant, and of course it's symmetric by definition, and therefore you can use Spielmann-Tang to solve it in nearly linear time. Okay, so we do know that, but in general, without this condition, then I do not know. This is all I'm saying. I actually haven't tried this at all.
You guys have a solver for one Laplacian.
Sorry?
You guys have a solver for one Laplacian.
In a special case where we have a three-dimensional simplicial complex that's convex. But I don't know but in general, I don't even know how you find, quote, a flux that meets a given demand on the edges, right? So
I see.
you're assigning a
Sure,
value
sure.
to the triangles.
Yeah.
And you want that to induce a curl on the edges.
Yeah.
So you can sort of, in the end, prove that you need to find one of min energy.
I see. So I have to confess.
Corresponds to when you get all done, but we don't know how to find just the first flow, just any flow.
Okay, so
Other than the special case where it's collapsible.
So I have to confess that I've really not looked into this at all. So it's just I want to say something that's sort of maybe some relevance to the workshop people, and that's the only reason I talk about this. But it's not. But
Is this someone else's work, or this is
no, it's something that we talk about. Cheyenne and Yuan and I talk about this. And we're going to write a proposal on this, and if it's funded, then we'll definitely have plenty of money and time and people to hire to work on this.
something you'd like to do, or something?
Yes, something that we would like to do. Yes.
They
Yeah.
didn't implement it.
No, you mean solve. I mean, give an algorithm.
Yeah, they didn't implement. They didn't implement their.
That's right.
Anything.
No, but just what's the algorithm? It says it's solvable in near linear time.
Oh, it's this algorithm. Okay, let's say there is an algorithm, right? And Spielmann-Tang proved that there is such an algorithm that if I give you a diagonally dominant symmetric matrix, I can invert it in nearly linear time, right? You agree, right?
Well, you can solve them, right?
Yeah. In this case, this matrix, delta 1, is going to be diagonally dominant if the Ricci curvature of the graph is non-negative. So you can solve it in nearly linear. That's all I'm saying. Exactly how to do it. In fact, I don't even know how to do this, to be frank. I just roughly know the idea.
That's a whole.
Yeah.
Just so you guys are, since you're both here, Gary does know how to do it. So it's
Okay. All right. Yeah.